Is it on? Yeah. So I'd like to thank the organizer for giving me this opportunity to present this thing in Bangalore. So I'm going to discuss some very elementary mathematics. So in this talk, G will be finite Abelian groups. Of odd order. D. And but the main focus is already too complicated. The main focus is the cyclic group, the element. So, and the aim is to say something, not to understand, because I don't understand, but to say something on the following convolution equation. So it's you have f from G to C, which is a non-zero function. And lambda, which is a complex number. And I want to know what are the solutions of the following equation, which is I'm looking at this finite sum, which is in fact the convolution of f with itself at the point 2. And I'm looking at the equation. I want this convolution to be proportional to the square. For all elements. So if this is the case, I will say that lambda is critical on G. Full value G. And F, a lambda critical function. Okay, and I will say D critical if G is Z over dZ. Okay, so maybe a small motivation. You may wonder why I have 2x here instead of 1x. We think of similar equation over the real number. The Gaussian functions are not solution of the equation with 1x. The solution is 2x. Because if you take a Gaussian function, you take the convolution with itself, it's a larger Gaussian function. When you take the square, it's a more concentrated Gaussian function. So, but it's 2x, it's a solution. So the Gaussian function are solutions. Another reason why it's nice to have a 2x is that this equation is invariant by translation. That will not be the case if there is only one. And but the main reason is that when you do computer experiment with a small value of d, you will see that the solution of this equation are very nice, 2x, but not with 1x. And this is because I have seen that the computer gave me nice solution, but I wanted to understand this question, which is very elementary. And so it's really completely elementary, but the partial solution I will show you today, in fact, relies on deep mathematics, elliptic curves, Abelian varieties, theta functions on these, and the modularity property of these theta function as a function of the parameter tau. So this is the plan of the talk. So let me tell you first preliminary properties of these lambdas that you can check easily. The first, if you apply Cauchy-Schwarz, you get that lambda is at most d in absolute value for such a critical function. So from that, you get easily a corollary. So the set of lambda is a constructible set, so it cannot be bounded except it's finite. So there are only finitely many critical values. D. Okay, and but it's like eigenvalues. You see, when you express that you have a matrix and you look at the eigenvalues and eigenvectors, there are always only finitely many eigenvalues, but the space of eigenvectors may be high-dimensional. Here also it will be the case that for a given critical value, there might be a high-dimensional set of lambda critical functions. All G. This is for all G. And another property, if you apply a Fourier transform to this equation, you get similar equation, but it's d over lambda, because the lambda goes on the other side. So d lambda is also critical on the dual group, but the dual group is isomorphic G. So that's nice. And this equation has an integer coefficient. So the Galois conjugate of lambda, 2. There are also over Q. Yeah, because this equation is defined over Q. It's yeah, so if you replace lambda by a Galois conjugate, you just replace f by the Galois conjugate, and it's still solution of this equation. And the last remark is instead of applying here, I have this bound for the absolute value by applying Cauchy-Schwarz inequality. But if you apply similar bound for all the non-Archimedean eigenvalue, you get that in fact lambda is algebraic integer. And even better, you get that it's a node algebraic integer. So what you get is that lambda minus 1 over 2 is an algebraic integer. So that's kind of nice because on one hand, lambda is an algebraic integer, but d over lambda is also an algebraic integer. So there should not be that many lambdas. Okay, so then what I do, so this was just a preliminary. The corollary is because the set of lambda is a corollary of this first assertion. Okay? The set of lambda is a constructible set. In the sense of, sorry, and it is bounded. So, but a constructible set is either finite in C. It's either finite or it's complementary, it's finite. It's obtained by elimination. It's a set which is obtained by elimination. So it has either to be finite or its complementary has to be finite. So but let me show you what the computer told me for d equals 11. So I asked it the computer for d equals 11. So it's prime, so it's just a cyclic group. And here is a list of all the critical values. And so it begins by lambda is equal to 11. There is lambda is equal to 1. There is, and I think you will like this list. It's up to Galois conjugacy. I will not write the plus or minus of the Galois conjugacy. There is for d is equal to 11. Lambda is equal to 11. This is the first. This is for f equal 1. That's the function constant equal to 1. It satisfies all those is 1, 11 times. It's 11 times 1. And lambda is equal to 1 is for the function f. It's equal to the Dirac mass at 0. It's 1 at 0, 0 at square. So then you have as a critical value for the square root of 5. You have lambda is I square root of 11. So all these are kind of trivial. This one is because you just look at f equal constant outside 0. And here you just take the Gaussian. F of x is e to the 2I pi x squared over d. That's the Gaussian. And it's very easy to plug this here. Woof. And then you have x plus y squared plus x minus y squared. They disappear. And then you get a Gaussian sum. The Gaussian sum is equal to I square root of 11. Okay. So those are the easy ones. And then the computer gives you 3 others. And now look at them, because we will spend the whole talk on these 3 remaining ones. So it gives you lambda is 2 plus I square root of 7, and lambda is 2 square root of 2 plus I square root of 3. So here you have square root of 4 plus I square root of 7. 4 plus 7, 11. Here you have square root of 8 plus I square root of 3. 8 plus 3 is 11. All those are, so this is the first two, and the last one is even more strange. Its lambda is 1 plus square root of 5 plus I square root of 5 minus 2 square root of 5. Okay? So it's a nice algebraic integer. If you take its modulus, the square of the modulus is 6 plus 2 square root of 5 plus 5 minus 2 square root of 5. So it's 11 of modulus square root of 11. Sorry? Yeah. So thanks you. This is what the computer tells you. It gives you, you can ask your computer, it gives you also formula for f, but then it's very complicated. You cannot see what's happening. So it's very easy to see that the lambda are given by this simple formula, but for the f, it's more complicated. So the question was how to prove mathematically that what the computer shows you works for every d and what the general setting. And to interpret even for d equal 11, this formula, I see only one mean is to use elliptic curve. And to interpret this number, I need Abelian variety. And this is what I want to do with this talk, just explain these values. No, those are Abelian varieties over C. And so let me tell you in one word all the proof so that you can relax. And so what you do is you interpret this group Z over dZ as part of a torsion group in some Abelian variety. Okay? On these Abelian varieties, there are some bundles whose sections are theta functions. And these bundles are given by equivariant condition in some direction, but there are some directions for which it's invariant conditions. They are periodic. So you choose your G as in this direction of the periodic part. And so you just restrict the theta function to this subgroup. And this will be the F. But then you have to check that this theta function satisfies the functional equation. Okay? And then you have to choose very carefully the parameter tau, which live in the Siegel upper space. Very carefully, I will explain, so that the functional equation is satisfied. So the Abelian variety, for elliptic curves, those will be always elliptic curves with complex multiplication. And for Abelian variety, you will just get Abelian variety with one Q endomorphism, which is unitary. So this is my talk. No. This is not the complete list. So I had the feeling that maybe always the long, except say for D prime. So let me write my today's conjecture. For D prime and the lambda not 1 and 11. Not 1 and D. And so also there is this one, but forget about this one. But at least my conjecture is that the only thing I still expect about the lambda which occurs there is that the minimal polynomial of lambda is kind of reciprocal in the sense that lambda and D over lambda are conjugate, Galois conjugate. I expected for a while that except for the value, which is this one, which corresponds to a function which is a constant outside 0, which exists for any D. There is a value, you can write the formula. And I expected that always the lambda was a Bell number. All these Galois conjugates are of a modulus square root of D, but this is not the case. But there are counterexamples, but there is still something. If you remove, here I remove these two. If you remove this third one, I always, in all the case, lambda has one Galois conjugate, which has absolute value square root. But this is what that's what the computer tells me. Now I'm going to so I'm stating the general proposition so that you see you write D. Sorry, not right here. Sorry, no. This one is the complete list. For 11, yeah. The computer told me that, yeah. You can ask the computer, I can tell you for up to 11. But if you write D is equal to A plus B, and with some congruence mod 4 on A, like we have here, not every A occur, then lambda equals square root of A plus I square root of B is D critical. Mod 4. This condition mod 4 is you start from the Gauss sum. So depending on D, the Gauss sum will be I square root of D or square root of D. And then you move by 4. You decrease or increase A and B by 4 so that the sum is constant. A plus B is D. Okay, so this is the proposition 2. And all those will be explained thanks to elliptic curves. And proposition 3 that I will be able to explain only with Abelian varieties. If you write D is A plus B plus C, so this one is kind of optimal. Here I'm not giving you the optimal statement, just a simpler one. And you assume A, B, C are integer, all equal to 1 mod 4. And B square minus 4AC is positive. Then lambda is the square root of A plus the square root of C plus I square root of B minus 2 square root of AC is D. Integer, positive integers. Positive integer, important. So this contains this case. A is 1, C is 5, B is 5. Yes? 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 Is D critical? D critical means critical over Z over DZ. Thank you. I had a conjecture that it should be D plus 1 over 2, but very recently I found a counterexample, so no, I don't. Yeah, for sure, if you control the degree, since you know it's an integer, and D over lambda is an integer, then you have very few values of lambda to check. It's very nice. But I don't know. Sorry? No, I said the opposite. I said the opposite. Long time ago, I expected that, up to the point where I found a counterexample for D equal 17. It's not a unit because there is lambda and D over lambda. Okay. What I'm saying is that in every case I know, okay, the polynomial is of the form it's equivalent to that. Okay. Lambda and D over lambda regular conjugate. I can say it in terms of polynomial, but you can do it by yourself. So let me go on. Now I want to think I want to give the proof of this. Okay. But I plan to give the entire proof. Okay? But before that, one has to see what is the theorem. I mean, like those are just examples. So I will give you now a general theorem. I will give you start with an Abelian variety, and I will give you a number, and it will be critical and some group G. So what is the general construction? Is Sorry, no, not far from a complete list. Even I will give more here, and it will still not be a complete list because all the number I will give you in this talk will be vain number. But I know there are counterexamples. Computer told me that. The computer told me that. I mean, you know Grobner basis. Okay, using Grobner basis, you get the polynomial, and you can do that. There are. It's kind of you have not so easy because you have 12 variables. So you have to look at 12 variables, degree 3, but you can manage to make it work. Yes. That's another way to say it, yeah. A complete list or all the numbers, that's another way. Meaning up to Galois conjugation. I said you have to plus or minus. Yeah, and now what is the theorem? Okay, so A omega is a principally polarized Abelian variety. Things elliptic curve if you want, dimension 1. This means that A is equal to Cn over lambda. Another way to say it, lambda lattice. And omega is the imaginary part of H. H is Hermitian, positive infinite. And omega is integer on lambda. And this is a polarized Abelian variety, and principally polarized means that the determinant of omega one, meaning lambda is autodual for this symplectic form. Okay, and then I recall what is the ring or the algebra of endomorphism. So A, not A, the Q endomorphism of A is the set of nu. So it's just a set of, you want to put the endomorphism of A in some algebra. So you tensor over Q. You can interpret them as a set of endomorphism of C, N, such that nu of the Q vector space defined by lambda is still in this Q vector space, where lambda Q and I will say that maybe there is a remark. No, sorry. The restriction of nu to lambda Q, I call it H nu. So is called the holonomy. It's nice to call it the holonomy of this Q endomorphism. So it's a usual game in Abelian varieties to play with two kinds of matrices. Either n matrix, n times n matrix with complex coefficient, or here, because this is a Q vector space of dimension 2n, a 2n times 2n matrix with rational coefficient. And you remark that, important remark for me, an exercise is that nu is unitary for the Hermitian form if and only if the holonomy is symplectic. For omega. So now, what is the main theorem of this talk? Is that if you have, if nu is unitary, so you are given a principally polarized Abelian variety, if nu unitary satisfies a condition, I call it star, which is a sorry. No. Omega of no. As a group transformation, no. Omega of h nu x is omega x, not at the Lie algebra level, because unitary is so unitary. Yeah. Thank you. Please ask questions. Thank you. Sorry? There is, yeah, xy. You can, yeah, xy is better. Thank you. And so this is the data. And then what will be the group? Let G, which is say lambda divided by lambda intersection nu lambda. Sorry, I will explain later. It's some condition to satisfy modulo 4. So it's what will give you the condition modulo 4 you have here. Okay. And to give a better answer, it will be related in the fact that in the theory of theta functions, the group of transformations for which the formula for transforming theta functions is not the whole symplectic group, but a finite index subgroup, which is not exactly those which are equal to identity modulo 4, but there is a strong another condition on the matrix, which is called Iguza subgroup. So this is what will occur. And it will correspond exactly to this kind of modularity condition here. So G will be this group. It's a finite Abelian group. It's not always cyclic. But the game will be to find unitary endomorphism in your semi-simple algebra here, and such that this quotient is a cyclic group if you want to get a cyclic group, and you will be able to manage for these cases. And then what is the conclusion? Then, sorry, let me finish the theorem. Then lambda, what is the value of lambda? Kappa. So it's a square root of d because it will be a Weil number. So absolute value is square root of d. But then there is a part of modulus 1, which is just the determinant of this unitary element. Determinant is Cn of nu, but there is a square root. And this is a critical on G. And with there is some kappa, which is the eighth root of unity. If you know the theory of theta function, there is an eighth root of unity that is difficult to write down. So you can write it down, but better to write it like that. And then what is star? So star, if you write H nu is as a block matrix, alpha, beta, gamma, delta, in a symplectic basis of your lattice. This condition tells you that H nu is equal to 1 mod 2, and the diagonal of gamma and beta are equal to 0 mod 4. So this is So, and you have to think of these conditions as condition in Q2. So those are rational numbers. So you embedded in the Q2 and okay, this is the theorem I want to explain to you. How much time do I have? 15 minutes? Ah, so 15 minutes. Yes, as a consequence of star, I think. I think as a consequence of star. I'm not 100%. Maybe you have to add it, but I don't think I. Okay. Assume G has odd order, but I think it's a consequence of star. And you can write this group as you see nu minus 1 lambda plus lambda over lambda. So you can really think of this group as a part of the torsion group of the Abelian variety. I think of it as being in the Abelian variety. So now I have to prove the theorem. So let me begin the proof of the theorem, give you the key lemma. So you write your Abelian variety, sorry, your lattice as 2Zn plus Cn, so inside Cn with so this is a so-called Riemann condition for us to be an Abelian variety. So not any lattice will give rise to an Abelian variety if n is larger than 1, but if n is equal to 1, all of them will do. And so tau has to be in the upper half space, so which means that tau is in Hn. It's an n cross n symmetric matrix. N times n symmetric complex matrix with the imaginary part. So positive, it is a n times n symmetric real matrix. You assume it is positive definite. So when n is equal to 1, it's just a Poincaré half plane. Okay. And this is called the Ziegel upper half space. And it's isomorphic Hn is isomorphic to SPNR over SPNV. Sorry, over SUN. So it's maximal compact subgroup UN. And if you have an element sigma here, that you write alpha, beta, gamma, delta as there, then the action of SPNR on these matrices is given by the usual formula that you know in Poincaré upper half space, which is alpha tau plus beta divided by gamma tau plus delta. This is the formula for the action. And now I have to introduce the theta function. So say for Z Cn, I want to give to you the formula for theta of Z and tau. That I write also theta tau of Z. That's a function of Z. And it's a periodic function in Z. So you'll develop in a Fourier coefficient. The sum for M in, for M in Zn. There is just a Fourier series if you are dealing with an elliptic curve, if n is equal to 1. And so there is this periodic phase, e to the 2I pi transpose M Z, which is the sum of Mi Zi that you have in the exponent. M is M1 Mn, and the Fourier coefficient is a Gaussian. This is what theta function are that you write on the form e to the I pi transpose M tau M. This is a quadratic. So this gives you a Gaussian when M moves. Okay, this is the formula for the theta function. Those are sections of bundles on the Abelian varieties. They are not functions on the Abelian varieties. They are not invariant, but they have some equivalent properties. And this bundle, that when you define its space of section, is 1. The dimension is 1. That's why the theta function is very important. Okay, so now what's the key lemma that proves the theorem? And so let me introduce the, sorry? Tau is a matrix, a symmetric matrix. And then a scalar product with transpose of M. And then, yes, I think of this tau as a, since it's a symmetric matrix, I think of it as a quadratic form. So I'm computing, this is, you want to see what this is. This is the sum of Mi, Mj, to Ij, sum over Ij. Yeah. And this is, this quantity is the sum over I. I is from 1 to n. Here, Ij are from 1 to n. And this is the sum over I of Mi Zi. Okay? If you think n equal 1, elliptic curve, which is very important because it gives you the example square root of a plus I square root of b. If you think of that, then here you just have e to the 2I pi mz. M is just an integer in this case. And z a complex number. And here you will have e to the I pi tau m squared. Usual formula for the Jacobi theta functions. So those are Riemann theta functions which generalize Jacobi theta functions. So what is the key lemma? The key lemma is under some assumption, okay, that I will write later. And I want to introduce a group for you. So I introduce a matrix, let D, which is a diagonal matrix D1, Dn, and with D1 divides Dn. Those are integers, positive integers. And then I can introduce the group G is D minus 1 Zn over Zn. So any finite Abelian group can be realized as such a group G. Okay. And so the k-lemma tells you that the function for all z in Cn, the translate by z of the theta function restricted to G is critical. Since W to theta tau of Z plus W is critical on G. Okay, this is what the theorem tells you, and for which value of lambda, and for lambda is equal to, there is some kappa, which is the eighth root of unity, and then I have to write you the number, but I have to tell you how you have to choose tau. So this theorem will not be for every tau. So you need one assumption, which corresponds to that the fact that G is obtained thanks to this unitary transformation. Okay? But I told you that okay, so the assumption is the following: is if you are able to find sigma in SP and Z, but with some modularity condition, which is in fact you are in the Igusa subgroup. So I write it theta 2. I will define theta 2 later on, but it's just exactly the element of SP and Z that satisfies this condition, this modularity condition. So if you are able to find an element of gamma theta 2 such that sigma applied to tau is in fact correspond to in fact to a finite index subgroup of I mean to an isogeny there is of your Abelian variety, so meaning more precisely it's d tau d. If you are able to find such sigma, then your translate of theta function will be critical and restricted to this piece of the torsion subgroup, for which value you compute kappa is the square root of something like determinant of gamma tau bar plus delta. There is -1. Kappa 8 is 1. Okay. So for all Z, this is where it's nice, because I told you there is only finitely many critical value, but it's like eigenvalue and eigenvector. Okay, sometimes there are multiplicities, so you really have to think of these critical values having high multiplicity, because here when you are dealing with n-dimensional variety, you find like n-dimensional space of solution. The whole Abelian variety embeds in the projective space of critical function. You think of it as part of the projective space. Okay, that's the statement. Gamma theta 2. That's the Igusa subgroup I have to define. Thank you. So yes, gamma theta 2. I said it. Yeah, that's those matrices. I changed this. Okay. Gamma theta 2 is a set of sigma in SP and Z. That satisfies exactly the same condition. SP, yeah, I mean, okay, whatever. Yeah, you're 2n. SP and Z that satisfies this condition. Okay. And now let me say just one word how this key lemma implies a theorem. Okay, so here we are dealing with some unitary transformation. Okay, but you may think, yeah, the nth, yeah, okay, that's a question of convention. It's SPN, rank n. The rank is n. Rank n. The rank is n. Okay, if you want. Right. Then what I want to say, maybe I don't say it, but I want to say, I just want to point out something which is that I find very nice before going on. But I will not say what you can imagine that it implies a theorem. And what I want to say is, okay, one of the simplest critical value example is d is equal to 5. Okay, and so the c plus lambda you get is lambda is 1 plus 2i. So the question is what is the simplest value of tau for which this theta function will satisfy this kind of condition? You want sigma tau is equal to 25 tau. Tau is an element of the upper half plane. And the answer is tau is minus 7 plus I over 25. Okay, so this is the tau you have to choose to get this value. If you don't know that you have to look for this equation, it's not so easy to guess what will be the tau. That's what I want to point out. Okay, so now maybe I gave the 3 steps of the proof to follow me. Okay, so I just say it. Okay, so the 3 steps of the book is you open a graduate book on Abelian variety. And if you read all the graduate book, you will see in this book there are three important formulas. The first formula is Riemann addition formula, which relate the theta function in z plus w times the theta function in z minus w. In terms of sum, decompose it. The second important formula is the isogeny formula, how you relate theta function for isogenic Abelian variety. And the third important formula is the so-called transformation formula, which tells you how the theta constant, theta of 0 and tau, depends on tau when you let element of SPNZ act on them. And so the formula do exist, but they are particularly nice when so you want to relate that when sigma is in this Iguza subgroup. And so the proof is you apply successively these 3 formulas. And that's it. Thank you.
All right. Thank you very much for a great talk. Are there any questions?
So are you sure, did you only find one counterexample which wasn't a Vane number?
Do I have one counterexample?
I mean, I'm saying the non-Vane number, did you only find that once? Or do you have other examples where it fails to be a Vane number?
I just have one. But
is it possible the
no,
computer...
maybe I have 2.
Okay.
Maybe I have 2. I think there will be infinitely many, but
okay.
I don't understand them.
But you trust the computer
really,
on those?
Sorry?
You trust the computer is correct on those?
Yes, 100%.
Okay.
100%.
Okay.
No,
okay.
100%. I mean, it's so impressive that I mean, you see, the computer for d equal 11 gave me this list. I was not able to understand why he was able to find 2 square root of 2 plus I square root of 3. Okay, and then I was able to prove it through elliptic curves, but I didn't tell the computer. I think there is maybe an elliptic curve somewhere, and And also what I want to point out is that even if you are dealing with higher dimensional Abelian varieties, if you choose carefully this matrix, this diagonal matrix, like with 1, 1, 1 dn, and you solve this equation with sigma in this finite index subgroup, then you get a critical value on a cyclic group. And this is the way I prove proposition 3. There, and also what another thing I may say is that there are very nice Abelian variety, which are called Abelian variety with complex multiplication. And so if, and it has the following corollary. If you take S, an integer in a CM number field, and you compute 1 plus S minus S bar, then the reflex norm of this guy is a critical value in a group which is associated with this number. So it has something to. Yeah.
So your assumption was D is not necessarily prime, right?
D is what?
Not necessarily prime.
Yes, yes, exactly. This is why I when I was studying the computer experiments, okay, I saw that he got these nice values, not only when D is prime, but also for number D like 15 or 9. So really, I thought the only part of mathematics where you don't assume that D is prime is when you study torsion subgroup in Abelian in elliptic curves or Abelian varieties. So yes, that's where I wanted to go there.
And anything special happens for primes, or no? It's like nothing.
Yes, because prime. This is why my conjecture is about prime. See, I have a conjecture about prime. The reason is that this subgroup, they give you parasite critical value, and because which come from subgroups. So
thank you.
So here in this in the lemma in the theorem, you could take capital D to be 111D.
Yes,
and then you
yes.
always have. So
yes. And this gives great example. Yeah, I have a nice example with n arbitrarily large, where you can working with number field, CM number field, and for which you get the following critical value, which is a product of 1 plus 2i sine something like 2 pi k over p. P will be a fixed prime, and the product is something like product from k equal 1 to p minus 1 over 2.
So this is an eigenvalue?
And this is D critical for some D, and for that you have to use exactly the group to say 1, 1, 1.
But it doesn't follow from your theorem.
Sorry?
It does not follow from your theorem, because here you get the quadratic. I mean,
it follows from this theorem. No, it follows from this theorem, because you see, theorem in the theorem, instead of this, you have you have this square root of a determinant. Okay.
Okay.
Square root of a determinant. Determinant is a norm.
Yeah.
When you take the square root of the absolute value of the determinant is the norm, but when you take the square root, it's a reflex norm. So what I'm doing some kind of product of not every conjugate, but just half the conjugate. So this is the reflex norm of some guy.
So last question is, suppose D is prime.
Sorry?
My last question is, suppose D is prime.
Yes.
So here you found many examples of critical, D critical.
Yes.
So do you expect that this accounts for most of them, or you think that you're missing some other?
I don't have enough. Since for a while I expected all of them were Bell number, and then so I don't have enough computer evidence.
because if you write down all the minimal polynomial of lambda over z, so you can write down the factorization of
Yes.
and so do you understand the factors? Do you have an idea of how large the largest largest
Thank you for asking, but my answer is I think I have told you all what I
Okay. Thank you.
all what I know on this topic.
Right. Any other questions? There is one more.
Sorry, a stupid question. So, what happens when D is even?
D is even. You don't want to go there because because you see there is this multiplication by 2, and then it's not injective, so it gives you some. It gives you that I forgot, but that maybe if you have two guys which have same number, either the function f at that point are equal or they are opposite. And so you have, and then you have to divide into according to the sign, and and then it doesn't give you anything nice. I mean, the computer doesn't give you any nice answer. So it was really better to restrict at the very beginning the case where D is odd. And when you see that things are not going well, then you make the assumption that make the theorem nice.
Right. Maybe I can have one more question.
Wow.
Namely, we started with a problem that indeed looks very much like an eigenvalue problem.
Yes, but non-linear one.
Non-linear one. So my question is, what actually made you study this particular formula? Why square of convolution and like square convolution and square on the other side?
Well, I was focusing on another problem. I was stuck for 6 months, and this problem involved like z over d squared times z over d squared, z over d cross z over d. So it was very difficult to do computer experiment because even when d is 5, since you are dealing with z over d cross z over d is 25. So I thought, what is a simpler problem that that is of the same kind? So it was really a quadratic equation depending on very much this form. And so since I was doing computer experiment with a more complicated problem, when I was very quickly I was able to implement it less than a few hours, less than half a day, and then I got the nice answer. And then I thought, as soon as you see the nice answer, you want to focus. And so I forgot about my problem. And this problem is called equiangular lines. Equiangular lines.
All right. If there are no more questions, let's thank the speaker again.